Welcome. This video kicks off a 500 question deep dive into generative AI and large language model technology, each question answered and fully explained. Question 1. How does a transformer's decoder pull relevant information from the encoder outputs when generating the next token? Answer. Integrates information from the input sequence into each decoding step by a learnable, context-dependent weighting of encoder values. In the encoder-decoder, aka cross-attention, block of a transformer, the decoder does three things. 1. Forms a query, Q, from its current hidden representation, which encodes everything it has generated so far. 2. Uses the encoder's outputs as keys, K, and values V. 3. Computes attention scores by taking scaled dot products between Q and every K. After a softmax, those scores become weights that tell the model how much of each encoder value to mix into a single weighted sum. That weighted sum is then fed back into the decoder layer. In short, cross-attention's QKV weighting is the core trick that lets the decoder selectively pull information from the encoded source sequence. Question 2. What pre-training objective does ELECTRA introduce that sets it apart from classic masked language model transformers? Answer. A key innovation of ELECTRA is its replace token detection pre-training task, where the model learns to distinguish between original tokens and tokens that have been replaced by a small generator network. Question 3. Which issue frequently complicates the distillation of large BERT models into compact students? Answer. A common challenge is selecting the appropriate temperature for soft label distillation. In knowledge distillation, the teacher network's soft probability distribution over classes or token predictions is passed to the smaller student model. That distribution is smoothed by dividing the teacher logits by a temperature T before applying softmax. If T is too low, the distribution becomes almost one hot, so the student receives little extra information beyond the hard label. If T is too high, the probabilities flatten out so much that meaningful differences between plausible alternatives are washed away, giving the student noisy or uninformative targets, because optimal T depends on factors such as task type, label space size, teacher-student capacity gap, and even batch size. Picking the right value often requires extensive grid searches or heuristic tuning, making it one of the trickiest practical hurdles when distilling large BERT-style models into compact students. Question 4. When a text classification model encounters a word that wasn't in its training vocabulary, what embedding strategy does it typically fall back on? Answer. By using random vectors. Most traditional word embedding layers, e.g. word2vec, glove, fast text in word-only mode, are built around a fixed lookup table. At inference time, an unseen term has no entry, so frameworks fall back to a dedicated unknown or UNK row. This vector is initialized with random numbers, often uniform or normal, and then treated like any other embedding parameter. During subsequent training or fine-tuning, the UNK vector receives gradients and can adapt, letting the model learn a single catch-all representation for all rare or novel words. Dropping them would shift word order and break positional information. Supplying something preserves sequence length. Why not average neighbors? That would leak context from the current sentence into what should be a position-wise, reusable embedding. Modern twist, subword tokenizers, byte pair encoding, word piece, sentence piece, greatly reduce true OOV events by decomposing new words into smaller, known chunks. But when a token is still unseen, the random UNK vector remains the safety net. So the pragmatic default across many NLP toolkits is map every OOV token to a single randomly initialized vector that gets updated like the rest of the embedding matrix. Question 5. How do dual-encoder architectures leverage embeddings to perform semantic search? Answer. They create embeddings for both the queries and the candidate documents Then measure the similarity between those embeddings, e.g., cosine or dot product, to rank results. A dual encoder, sometimes called a bi-encoder, has two almost identical transformer stacks, one for queries, one for documents, that each compress a text sequence into a dense vector. Documents are encoded once offline and stored in an index. At runtime, only the user query needs to be encoded. Retrieval then reduces to a fast vector similarity lookup, often dot product or cosine distance, between the query vector and millions of pre-computed document vectors. This design sidesteps the heavy cross-attention over query doc computation done by cross-encoders, enabling real-time search on large corpora while still capturing rich semantic information learned during training.